So simple shear stress.
Okay, so I'll continue with the simple shear stress equation. So as you took a small element, so which is going to cause the uh, twisting or oscillating of the surface with respect to the horizontal plane as well as with respect to the vertical plane. Okay, so now what will happen? So as you want to go for equilibrium state of the element, so an another couple is going to form here. Okay? Another couple is going to form. So then only your shape is under what the element shape. Otherwise, it won't get in a rectangular manner. So it may get in another manner. Okay. So now to get this ones, we have noted two type of stresses here. This what two faces. Okay. We have noted two faces. Okay. So I'll redraw diagram here. Now this is the one face. Okay. This is acting in downward direction. This is acting in forward direction. Okay. Now this is what face A, B. Okay. C, D. So as rise to shear stress will takes place on this BC. Okay. So again this try to make an rise on the surfaces. Okay. So let us consider the intensity of a shear stress which is going to act on this. Here it is a QAB. Okay. And you consider a element of thickness as T. Now this face is QAB. Okay. Now thickness of this entire portion is of what T. So dimensions are unit here. Dimensions are unit. That means 1. Okay. 1. Now. So now the considering the equilibrium of the element. So the vertical force on AB. Okay. So considering equilibrium of the element, the vertical force on AB. Okay. So this is equal to what? We made assumptions QAB as a stress, AB is the height, and T is the thickness. Okay. T is the thickness. Now you got an here vertical force. Vertical force. Okay. So now this can be balanced by the force which is acting on the surface CD. Okay. Which is acting on the surface CD. Okay. Now this can be balanced by the vertical force acting on face CD. Okay, that is what in downward direction. Downward direction. Okay. So now if you write here QCD equal to vertical force on face CD equal to QCD into CD into T. Okay, into T. So let us equate these two. Equate these two. So what will get? Now consider QAB equal to QCD equal to Q here. It is not a G, it is a Q. Okay? Q. Because the force which is going to cause on AB is upward direction, and that has to be balanced by the face is on right hand side, that is the CD. So let us term these stresses which are going to act on both the surface as a Q. Okay, Q. Now since QAB and QCD are giving rise to equal and opposite forces, rise to equal and opposite forces, that is what with moment arm AD, with moment arm AD. So now because of this, what happens, this try to rise this AB surface, now this try to down it and CD surface. Okay, now the moment which is going to obtain, so based on this another two surfaces, so what will get here, momentum arm. Now this will become a arm here, momentum arm. Okay. So what will get, couple of magnitude, equal to Q AB into T into CD. Okay. This is what, couple of magnitude. Okay. Again this can be balanced by another couple which is going to get over the surface AC here. Okay. Which is going to get on the surface AC, okay, and BD, AC and BD. Okay. So now this can be balanced by another couple. Okay. I think you are getting confusion. I will try to go for a simple way. Let us see. So don't have another book now here. Okay, so let us continue here. Just yesterday you have noted a diagram here. I will redraw the diagram. Now this is what face AB, this is CD. Okay, now it's going to form a couple here. Okay, with value of Q. Okay, so now arm is what, BD here. Sorry, I need to go to writing notation is different here. Now we will go here. Now AD is the arm here. Now we are going to get a couple here. This is what a Q, this is what a Q, right? You are getting a couple here. So now this couple try to rise the faces on both sides. That is what AB face as well as CD face. Okay, AB face as well as CD face. Okay, so to compensate this one, okay, so you need one more couple. Okay. So the thing is that in this simple shear stress theory, Q equal to Q dash, which is going to cause the couple in the clockwise direction as well as in an anti-clockwise direction. So it is better to understand with the clean diagrams within some example. Okay, so I will leave this topic here only. After making some models, I will show how you can get this equation. Okay, ಸೊ ಇದನ್ನೇನು ಮಾಡ್ತೀನಿ ಅಂದರೆ ಒಂದು ಮಾಡೆಲ್ ಮಾಡ್ಕೊಂಬರ್ತೀನಿ. ಮಾಡೆಲ್ ಮಾಡ್ಕೊಂಬಂದು ತೋರಿಸ್ಬೇಕು ನಿಮಗೆ. ಇದನ್ನು ಒಂದು ಸಿಂಪಲ್ ಮಾಡೆಲ್ ಅಂದರೆ ಕ್ಯೂಬಾಯ್ಡ್ ಟೈಪ್ ಮಾಡಿ ತೋರಿಸ್ಬೇಕು. ಸೊ ಇದನ್ನು ಸದ್ಯಕ್ಕೆ ಇಷ್ಟ ಬಿಡ್ತೀನಿ ನಾನು. ಇದನ್ನು ನೆಕ್ಸ್ಟ್ ಇನ್ನೊಂದು ಕ್ಲಾಸಲ್ಲಿ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತೀನಿ, ಸಿಂಪಲ್ ಶೇರ್ ಸ್ಟ್ರೆಸ್ ಥಿಯರಿ. ಸರಿನಾ? Are you hearing me or not?
Yes, sir.
Okay. So we'll leave this here only. Okay, we'll make one model and we'll discuss this one. Okay. So next, the next concept is the relationship between modulus of elasticity and modulus of rigidity. Okay. So relation between relationship between modulus of elasticity and modulus of rigidity. Okay. That is what relation between E and G. E and G. So now every elastic constant has a relation with each other. So now the Youngs modulus is related in relation with the modulus of rigidity. Youngs modulus is also in relation with bulk modulus. Okay, in relation with bulk modulus. So you need to get the relations. What is the equation you are going to get to find out the either modulus of rigidity or either bulk modulus in relation with the Youngs modulus here. Okay, that is what relation between modulus of elasticity and modulus of rigidity. Now for this one, we'll just consider an element here. Okay? Just consider a element. Okay. So I'll draw one diagram here. We consider an element of unit size. Okay. So let us take this as A, this point as B, this point as C, this point as D. So now the diagonal BD, so it has an unit length A, so it is subjected to the shear stress at the top surface. Okay, that is what tau. Now so if you fix the bottom surface here, okay, that is what surface AD. Okay, now if the stress is applied on top surface, now whether it is going to deform in this way or not. So if you fix this surface, bottom surface here, okay, if you apply this stress on this top surface, whether this surface is going to deflect or it is going to remain same.
Yes, sir. Yes, sir.
It is going to move some distance. Okay, so now the deflection is going to cause the change in some dimensions here. Okay, so let us identify here. Now after application of the shear stress, now it has been deflected to new position here. So this is what a C dash, this is B dash, okay? C dash and B dash. So otherwise you take this as a new term. Let us go for this as a E. Let us this new point as a E. Okay? Now let us draw here. Okay. Now in this case A, D, C dash E is what a deformed shape. It is what a deformed shape. Okay. Now If you consider the diagonal length, if you consider the diagonal length here, whether the diagonal length BD is increased or it remains as it is. Whether the diagonal length increases or remains as it is. Whether diagonal length increases or it
Remains same, sir.
remains the same.
Remains same, sir.
Think it once again. Now earlier you just look out here, okay, its diagonal length is here, okay. So as the deflection takes place, so what is the new shape here? This is the new shape. Now it has been in some distance here. That is what this much distance has been elongated. Okay.
Yes, sir.
Okay. So now, if you consider the diagonal, okay, so you consider the diagonal. So now diagonal is going to make some changes here. Is going to make some changes. Okay. Now you just drop a line, okay, perpendicular to diagonal DE. The point has to intersect the B. The point has to intersect the B. Okay. What I'll do now, I'll just draw one line here from this point. Now this point is what a F. This point is F. Now you need to find out what is the strain in diagonal BD. Strain in diagonal BD. Now how will get the strain in diagonal BD? Now it is what a change in length to the original length. Strain definition, right? Is it right? Yes or no?
Yes, sir.
Okay. Now if we compare, now what is the original length here? It's the BD, original length. So let us consider the angle of deflection is a very small. Then we can consider the length BD equal to DF. BD equal to DF. Okay. So now how we will find out the change in length here? Delta L. So delta L is what? It is what? DE minus EF is a change in length. Are you agree this one? Change in length is what? DE. Now diagonal length is DE here, elongated diagonal length, minus EF or minus FD. Change in length ಬರಬೇಕು. Change in length ಬರಬೇಕಾದ್ರೆ ನಾ ಬರೆದ equation ಸರಿನಾ ತಪ್ಪಾ?
Sir, DE minus DF.
DE minus DF, right?
DE
So
minus DF.
now DE minus DF will give the change in length. Okay? So DE minus DF will give the change in length. That is what? Distance EF. That is what? Distance EF, right? So now let us substitute here. So EF divided by dB. EF divided by dB, right? Now as you consider, it has been unit element of dimensions. Let us consider side as a side as a okay. Now you find out what is the length dB. So now based on geometry, okay, now this distance is, let us go for this distance as A, this is also A. Now you need to find out what is the distance here. How you will find out? You just go for adding Pythagoras theorem here, okay, Pythagoras theorem. Now this distance is AD, this distance is AB, okay. So BD equal to what? AB square plus what? AB square plus AD square. Okay. Now BD square equal to, I'll go for 2 times AB square, because we have gone for unit dimensions AB equal to AD. AB equal to AD. Okay. Now what will get? BD equal to or D, BD equal to, okay, what will get? AB into root 2. AB into root 2. You check out the diameter, you check out the geometry. Okay. Now if you substitute in the above equation for strain in diagonal BD, okay, now this is what? EF divided by AB into root 2. AB into root 2. How will you get a root 2? By this equation you are going to get a root 2. Okay. Now, so now angle of deformation is a very small. Angle of deformation is a very small. So you can assume angle BEF. Okay. We can assume this angle as a BEF. Now because of deformation you are going to get a strain here. This is what? Strain, shear strain. We are going to get a gamma, or you can say it as a pi. Let us go for it as a pi. Okay. Now considering angle of deformation is a very small, okay, so let us notify the angle of the triangle BEF. Okay. Angle of triangle, write as assumption here, since angle of deformation is very small, we can assume angle BEF equal to 45 degree. Okay. Hence, what is the dimension of EF here? EF equal to BE into cos 45. Okay. Let us look out in diagram. EF. Okay. Now this is the dimension change in length EF is. Okay. How you are going to calculate? We have treated this angle as a 45 degree. Okay. We have treated this angle as a 45 degree. So then BF equal to what? EF equal to, so BE into cos 45. Just apply some trigonometric relations here. BE equal to, sorry, EF equal to BE into cos 45. Okay. So now let us substitute back again in a strain equation. What equation you got? EF, okay, right, divided by BD. This is equal to what? EF divided by AB into root 2. Now BE into cos 45 divided by AB into root 2. Right? No. So what will get by the relation here? BE divided by AB. If you look over the previous figure, what will get relation for this portion? Now here BE AB, what will get relation here? BE divided by AB. Trigonometric functions. We'll get a cot theta or we'll get a cot phi.
Phi, sir, cot phi.
Cot phi. Check it once again. So you have shear strain here, that is what angle of deflection is a pi. Okay, so if you consider this triangle, okay, now this is what pi.
Sir, cot 45, sir. Cot 45.
Okay, now this angle is this distance is AB. Now this distance is BE. Okay, now tan pi equal to what? Opposite side by base, BE divided by AB. Are you agree? Are you agreeing? No. Now I want to find out angle here. Tan pi equal to BE divided by AB. Are you agree?
Yes, sir.
Okay. So now look out here. Now tan pi equal to BE divided by AB. What you need? You need BE now. Okay. So now BE equal to what? AB into tan pi. Okay. AB into tan pi. So now let us substitute back here. B equal to what? AB into tan pi. Okay. Into cos 45 divided by AB into root 2. AB into root 2. If you further simplify this one, you are going to get tan pi divided by 2. Tan pi divided by 2. So cos 45 is what? What is the value of cos 45?
1.
Cos 45 value 1. Then cos 0 value is, okay, if you substitute the value of cos 45 here, okay, so now tan pi, now this AB get cancels here, okay, so what remains here below? Root 2. Now this is what? 1 by root 2. If you simplify this one, you are going to get, so strain, okay, strain equal to, sorry, strain equal to tan pi by 2. Okay, right. So as if you consider the deflection or deformation is a very small, so you can say this is equal to what? Pi by 2. This is equal to pi by 2. Okay. Now what is the shear stress relation or shear strain relation? So Q divided by G. Now in this case we have gone for tau. Tau divided by G is what? Pi. Is what? Pi. So let us just substitute it here. Okay. So strain along a diagonal BD is equal to what? 1 by 2 into tau by G. Okay. So because you note down, so strain equal to stress by modulus of rigidity. Here both the shear strain here, so here also shear strain, modulus of rigidity. Now you got one equation here. That is what the strain along diagonal BD is obtained by 1 by 2 tau by G. Let us notify this as equation number 1. Okay. Now, so in another directions what happens? In other directions what happens? Now in other directions what happens? Now just look at the stresses which is there on another diagonal, okay, which is tried to give. Now if you consider the stresses on this diagonal, okay, so what happens is try to compress, it tries to compress again, that is also going to give rise to the strain, that is going to be cause some tensile strain along the diagonal BD here. Okay. So one is what, because of the movement here you are going to get some deflection. So now there has to be accomplished with the help of the Q, which is exactly on right angles to this surface, okay, on this surface, okay, and on this surface you try to compress it, okay, and it will give rise to tensile stress, tensile strain. Okay. Now the tensile strain along the diagonal BD here, okay, tensile strain along the BD, okay. So because of these two stresses, okay, this is what, tau by E plus mu into tau by E, okay. This is what because of a direct, okay, because of the other directions which is a perpendicular to the initial one. Okay. Now if we equate these two equations, okay, if we equate these two equations, this is what second equation. Now equating equation 1 and 2, so what will get, 1 by 2 tau G equal to tau divided by E in bracket 1 plus mu. Now if you cross multiply, so E equal to, okay, 2 times G in bracket 1 plus mu. Now this is a relation, okay. This is what relation between, a relationship between modulus of elasticity and modulus of rigidity. Okay. Right. So next is the relationship between the modulus of elasticity and bulk modulus. So now for this one you consider an cubical element, yes. Consider a cube element, Okay, so which one is subjected to uniform pressure on all three mutually perpendicular directions. Okay. That is what in coordinate system x, y and z. Now, as you know, if stress is acting in one direction, okay, if the load is acting in one direction, okay, so it is going to cause two types of stress, okay, sorry, strain. One is what, a lateral strain, another one is linear strain. Okay. Now let us consider the stress in the x direction. Okay, stress in the x direction. So what is stress in x direction here? I will write stress in x direction. This is what P divided by E, sigma x equal to P by E, right? P by E. Are you agree or no? Are you agree this one? I have written sigma x equal to P by E. Are you agree? Are you agree? I have written stress in x direction sigma x equal to P by E, where a P is a uniform pressure which is going to act mutually perpendicular to each other, that is in direction of x, y and z. Now this is what a wrong answer. Okay, ಏನು ಬರೆದ್ರು ನೀವು ಕೇಳ್ಕೊಂಡು ಹೊಂಟ್ರಿ ಅಂದಂಗೆ ಆಯ್ತು. ಒಂದು ಏನು ಮಾಡತ್ತೀರಿ ನೀವು, ಸುಮ್ಮ ಕ್ಲಾಸಿಗೆ ಅಟೆಂಡ್ ಆಗ್ಬೇಕಂತ ಅಟೆಂಡ್ ಆಗತ್ತೀರಿ, ಇಲ್ಲ ಏನು ಯಾಕೆ ಹೇಳೋಣ ಕೂಡ ಅವ್ರು ಪೂರ್ತಿಯಾಗಿ ಅವ್ರು ಹೇಳ್ತಾರೆ, ನಾವು ಪೂರ್ತಿಯಾಗಿ ನಾವು ಬಿಡೋ ಅಂತ ಒಂದು ನಾನು ಆಗ್ತಾರೆ. ಇನ್ನೊಂದು ಏನಂದ್ರೆ ಎಲ್ಲ ಬಿಟ್ಟು ಗಪ್ಪನ ಮಕ್ಕೊಂಡಿರ್ಬೇಕಷ್ಟೆ, ಹೌದಾ?
Sigma equal to P by A, sir.
But in this case I said it has a uniform pressure. Okay, so what is the unit of pressure? What is the unit of pressure?
Pascal. Pascal.
Pascal equal to what?
Newton per meter.
Newton per meter square or Newton per mm square. Okay, so in this case it is itself is a stress here. In this case P itself is a stress. Okay, so now you need to find out the strain in x direction. Okay, now I will write here. So strain in x direction. Okay, now I will write here. So P by E, okay, P by E minus mu P by E minus mu P by E. Now why we gone for another 2 here? Because you have a stress in this y direction also. Let us take, if this is my x direction value, this is y direction value, this is z direction value. Okay. So all these stresses are in a positive way, all these stresses are at tensile. So they try to reduce the strain which is going to cause in next direction with the help of this Poisson's ratio, with the help of this Poisson's ratio. So let us notify here. Now this epsilon x equal to P by E in bracket 1 minus 2 mu. Okay, right? Now similarly in y direction, so epsilon y equal to, okay, so minus mu P E, okay, plus P by E minus mu P by E. Now this is what a strain in x direction, strain in y direction, strain in z direction. If you simplify it, you are going to get again small p by E 1 minus 2 mu. Now this is what a second equation. Earlier we have one equation here. Now this is what a second equation. Now if you write it for strain in z direction, you are going to get the same equation, P divided by E 1 minus 2 mu. Right? Now, what is the definition of a bulk modulus? What is the definition of bulk modulus? Yesterday I have gone through definition of bulk modulus. Bulk modulus definition entro stress by strain equal to bulk modulus.
Pressure by volumetric strain.
Yes, pressure by volumetric strain. So now let us rewrite here volumetric strain. Volumetric strain. So now this is what EV equal to. Yesterday I have noted EV is what, a summation of EX plus EY plus EZ. Right? Yesterday I have noted for rectangular bar as well as for circular bar. Okay. Volumetric strain is what, a summation of strains which are there in all three directions. Okay. Now epsilon x, epsilon y, epsilon z. Now let us add here. Let us add. Now Ex equal to what? This is P divided by E in bracket 1 minus 2 mu plus Ey equal to same P divided by E 1 minus 2 mu plus Ez is also same. Okay. Now how many times you got here? 3Pe, 3P divided by E 1 minus 2 mu. This is equal to what? Eb. This is equal to Eb. Right. Now by the definition of bulk modulus, K equal to what? P divided by Eb. Okay. Now let us substitute Eb equal to what? P divided by K. Right? P divided by K. Now let us substitute here. Let us substitute here. Okay. P divided by K equal to 3P divided by E 1 minus 2 mu. Now this P get cancels here. Okay. What will get equation? E equal to 3K in bracket 1 minus 2 mu. Now this is what a relation between Young's modulus and bulk modulus. Okay. A relation between Young's modulus and bulk modulus. Right. Next you have one more relationship between Young's modulus, bulk modulus as well as the modulus of rigidity. A relationship between Young's modulus, bulk modulus and modulus of rigidity. And modulus of rigidity. That is what EGK, a relation between EGK. So you have already noted two equations here. The relation between Young's modulus and modulus of rigidity is what? Right? And already I have noted. So the relation between Young's modulus and bulk modulus. Okay. Now in this case the common term here it is a mu. In this case the common term is a mu. Okay. So by any one equations you write the mu value and substitute it in any one equations, you are going to get the relation between bulk modulus modulus of rigidity and Young's modulus. Okay. Now, what I will do, I will consider first equation. Okay. Now, considering equation number 1. Okay. So, I will rewrite for mu. Okay. So, what will get 1 plus mu equal to, right, E divided by 2g, okay, and mu equal to E divided by 2g minus 1. Are you agree here? Poisson's ratio mu equal to E divided by 2g minus 1. Okay. So, let us substitute this one in equation B. Let us substitute in equation B. So, what will get? What is equation B? E equal to, okay, 3k in bracket 1 minus 2. Now, I will substitute it right here with different color, you can easily identify it. Mu value is what? E divided by 2z minus 1. Now, can you simplify the inner equation? Now, this is what 3k in bracket 1 minus E by g plus 2. Now, 3k equal to 3 minus, now this is a g, okay, 3 minus Eg, this is equal to E. Okay. Now, rewrite here again. If you simplify equation, E equal to, I will copy the above equation once again. Right. Now, what will get? E equal to 9k minus 3k E divided by g, okay, or 9k equal to E plus 3k E divided by g. If you further simplify this one, you will get E equal to 9 kg divided by g plus 3k. Okay. Now, this is what relation between the Young's modulus, modulus of rigidity, and bulk modulus, okay. Clear?
Yes, sir.
So, you need to make some practice over this one. So, you may get confusion while writing the equation for strains. One, because of the tensile strain which is going to cause along the diagonal BD, another one strain which is going to compress on opposite diagonal, that is also tend to increase the length. Okay. Nature is what? Because of compressive, you are going to get a one strain. Because of the shear stress, you are going to get a one tensile strain. Okay. If you just make a practice, you are going to get this relation. Okay. Right. So, you just give the attendance, just say present, sir. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, only 10 members. Right.
Post graduation students, we have this micro harness and shear bonds kind of test.
So you meet SMG Gini sir, whether he is there or not. Room number 1.
Right.